want to thank the organizers for giving me the opportunity to give a lecture here today, and also the Norbert Wiener Center for inviting me. So these are the two key words in my talk, Leibniz and Hölder. And I want to say one thing before I get started, is that I work about a few hundred meters, or even maybe, I would say at most 200 meters from where Norbert Wiener was born. But I really hope that this is not my deepest connection with this conference. I feel that, I mean, I'm a lover of Fourier analysis, and I really hope that, unfortunately, I don't have an applied aspect, but I hope that listening to your talks, I will enrich my my understanding of things, and maybe, you know, if any of you have some problems that are applied and have some theoretical questions and you want to talk to me, I'll be happy to talk to some of you as well. All right, so these two guys, I don't think they met, but mathematically they'll meet today. Leibniz's rule concerns a differentiation of the product. And so I'm going to just take a simple case where we take two derivatives and Hölder's inequality is this inequality that also has something to do with the product. And these are the usual LP norms, and the indices satisfy this relationship. Okay, so this talk, okay, so before I say this, so you can marry these two inequalities into one and ask, say for example, this one. How can you compute this one? Well, of course, you have the trivial inequality that you'll obtain if you use this identity, Leibniz identity, but there's also an inequality that, let me go with a higher order. You can obtain by skipping the middle order derivatives. Like this. So in other words, this term is not so important from the point of view of LP norms. So this is not so hard to prove. Maybe you can sit down and do a little exercise and prove it. But what I'm interested in today is discussing some sort of an analog of this in a fractional case, which is the case where the number of derivatives is not an integer, but it is some positive number. So one has to define, first of all, this operator of fractional differentiation. So S will be a positive number, and there's two ways. One way is by taking the Laplacian to the power S over 2. The other one is taking identity minus the Laplacian to the S over 2. This is two ways. This is the homogeneous, this is the inhomogeneous way. And so what this means is taking a function f, take its Fourier transform, and multiply by 1 plus xi squared to the S over 2, and then take the inverse Fourier transform. This one means you don't put the 1, you just multiply it by xi to the S, and then take the inverse Fourier transform. Now, heuristically speaking, this is taking all the derivatives up to and including order S. So the 0th derivative up to S. So this one is only the derivatives of order S. And so the question is, what happens if you take one of these two guys and you apply to the product of two functions? And so that's the question I want to address today. It's a question of smoothness. So what is the smoothness? I mean, how does the product reflect? I mean, how is smoothness reflected in the product? And so think about this for a minute. Now, convolution is an operation that has the following property. You take a bad guy and a good guy, and at the end you get a good product. So it inherits the good properties. But multiplication is something that doesn't do that. You take a bad guy, multiply with a bad guy, and then you inherit the bad properties, unfortunately. It's like, and so the smoothness is limited by the smoothness of the least smooth function. Anyway, keeping that in mind, you can ask the question, so what happens if you take the Hölder norm of this expression? So I forgot to say here that P, Q, and R are numbers that are between 0 and infinity. And in fact, they can be all the way down to 0, and they can even be equal to infinity. And it turns out that there is some sort of Hölder type inequality in this setting, and the inequality will be this one. But this inequality, first of all, we'll have a constant here, and second of all, is only valid in the inhomogeneous case. So this is for the inhomogeneous case, and for the homogeneous case is not right. Is not correct. In fact, it makes sense that it would not be correct because the thing I mentioned before about the smoothness. So. So the question is, what would be an analog of this inequality that would be true even in both settings, and something that would be possibly analogous to this one? And here's the and so this was a question posed by actually, I'll give you a little bit of history. It was posed by Cato in '86, and then there was some preliminary answer given by Cato and Ponce in '88, and there was another paper by Cato, Ponce, and Vega. Koenig, Ponce, and Vega. Sorry, different K. That was in '93. And that proved consider the cases or S is up to 1. And then there's another paper by Muscalo, Pfeiffer, Tao and Thiele in '04 that dealt with the case of the general S and okay, the case of general S. So the inequality is the following. At least I'm going to copy the inequality from this paper. That if you take the Hölder norm, you're going to get a constant. You're going to get one function LP times the other LQ plus one function LP times the other one LQ. And that is sort of analogous to this one. And, you know, it's a marriage of these two inequalities, this equality and this inequality in the case of fractional differentiation. So S here is positive, and P and Q and R are related as in Hölder's inequality. So what I want to do today is I want to give another proof of this, but the advantage of the proof I want to give is that it works. It gives you the sharpest possible range of exponents for which this inequality is correct. The sharpest possible range. And in fact, the sharpest possible range includes R, where R is less than 1. And maybe I'll state it as a theorem, and then I will explain to you why r less than 1 is important. Yes?
I'm sorry, which one is the,
Oh, yes, this one. You know what? It doesn't matter. You can switch them around. You can have P1, Q1, P2, Q2, and where the indices satisfy Hölder's inequality. Okay.
Quite different from the one over there. It has product. This one doesn't. So,
This one? It has a product.
yeah, but that one, you have a sum of, you have sort of binomial thing going on there, whereas here, it's a better inequality.
No, it's the same. It's really the same inequality, I think. Okay, so first of all, why r less than 1? Or maybe I'll state the theorem. So the theorem is that this inequality holds. This inequality holds if and only if you have P, Q, R between 1 and infinity, and R less than infinity, and R has to be bigger than n over n plus s. And this is sharp. So you see this is a number that's less than 1, and it's sharp. It's not true if it's less than this number. Okay, so this is joint work with Sengli O, who's my postdoc. And I want to point out that the case where all indices were equal to infinity was left open in our paper. The case P equals Q equals R equals infinity. That case was left open. And it turned out that soon after the paper was posted on Archive, maybe a few months later, I got an email from Bourgain, who told me that he knew how to do this case, and he published a paper on this together with a fellow called Dong Li. So even that case now is included. N is the dimension, sorry. This is all on Rn, so sorry about that. Should have said that. Okay, so why LR for R less than 1? Actually, this inequality, if you want, you can obtain from this inequality Hölder's inequality for Sobolev spaces. So you have something like this: FG W S R, which means S derivatives in LR, bounded by F W S P G W S Q. S derivatives in LP, S derivatives in LQ. So this inequality is a consequence of this one, because you can estimate this by the derivatives. So you wonder why is there a restriction on R? Well, that will come from the theorem. But why R less than 1? I'll tell you why R less than 1 is important. Because, first of all, interpolation works on LP for all P, the entire range of P's, from 0 to infinity. That's one well-known thing in interpolation circles. The other thing, people are afraid of LP for P less than 1 because they say, oh, well, multiplier theorems don't work. That's fine. They don't work. But here I'll give you the simplest example in the world. Take a spike. Let's assume it's compactly supported. X to the minus a third, dimension 1. You want to estimate how many derivatives does this function have in L1? Fractional derivatives. You say, okay, I know this function is in L3. Well, not quite, L3 minus epsilon. So this function has 0 derivatives in L3 minus epsilon. But also, we can differentiate it. Anybody can differentiate this function. You're going to get x to the minus 4/3 times the signum of x times minus a third. And this function will have, well, you can look at this and say, this is in L3 quarters minus epsilon. So it has one derivative in L3 quarters. which is less than 1 already. And so you see why somehow it appears. You don't want it. And then you say, OK, I can interpolate between these two and obtain that the function has gamma derivatives in L1. L1 is between these two spaces, and gamma will be 2/3. So actually, it will not be 2/3. It will be 2/3 plus epsilon, because there's a little bit loss of epsilon. So we have L 2/3 plus epsilon derivatives in L1. So that's what's going on. So that's why these things are important. So why is the theorem sharp? The theorem is sharp because there's a counterexample. And the counterexample came before the theorem. And the counterexample is take the simplest possible functions you can think of, e to the minus x squared in any dimension. And I'm sorry, the theorem is sharp, not always. It's sharp only if s is not an even integer. If s is an even integer, you can go all the way down to a half. But if s is an even integer, it's sharp. Because if f is not an even integer, it's sharp. Because when it's not an even integer is when you have a singularity here. When it's an even integer, there's no singularity. And then you have more smoothness, and then there's you don't have this restriction. So this example here shows that, in fact, if you compute, the product will be essentially the same function. And so if you compute the derivative, say, minus the Laplacian to the s over 2 of this function, it turns out, well, there's going to be two cases. You're going to get a polynomial times the exponential if s is not even. But if s is an even integer, you're going to get some other functions harder to describe, but this other function has limited decay. And this is the, sorry, this s even, s not even. This is x goes to infinity. If s is even is the case where you get Schwartz function. If s is not even, you get a function that has limited decay, obviously. And so there is this restriction. So you want to say, OK, what will this function be in LR? If you want this function to be in LR, you need to have minus n minus s times r has to be less than minus the dimension near infinity. But that's exactly this condition. In fact, if you have equal, it fails. So the theorem is sharp. And so what I want to do now is I want to spend maybe 5 minutes, 7 minutes to give you some ideas about the proof. So this theorem was published last year in Communications and PDE. OK, so the idea is to view the product, actually this operator acting on a product, as a purely bilinear operator. So if you do that, you can write it using the Fourier transform as a double integral So I'm doing the case of where this minus the Laplacian here. But this term works in both cases for both operators, the homogeneous and then homogeneous. And you see now why there's a difference. If s is an even integer, this is going to be actually a nice smooth function. But but if S is not, it's going to have a certain singularity of a certain order. Actually, we know exactly the order of the singularity when xi plus eta equals 0. So just to bring a, to think of this, maybe it brings some, signal processing language. We can think of these two as being signals. And then we're going to break them up into dyadic frequencies. That's something this audience probably understands quite well. And then we're going to have we'll encounter several situations. A situation where one function has a high frequency, the other has low, and things like that. So let's say that this is xi and this is eta. And this is f, and this is g. And so we can have a situation where you have a high frequency here, low frequency here, low here, high here. Or you can have the situation where we have both of them are low, or both of them are high. Now it turns out that in this case, there's no interference. This case or this case. So in other words, xi is bigger than eta, or eta is bigger than xi. If eta is bigger than xi, and this function vanishes, then that means and xi is 0, then eta will also be 0. So it will only vanish at one point. There will be singularity only at a point. That's at the origin. And it turns out, for example, when you have high-low, right? So what you do is you divide by the high, and you multiply here. So in this case, this function actually is not going to be bad. And you get the derivative of one function. So in other words, you're going to get a term like this. But you need to be able to control this one. Well, there's some multiplier theorems from the theory of bilinear operators. Maybe I'll mention some names. Koifman and Meyer consider the multiplier theorem of this type that would handle this. They did it for r bigger than 1. And the case for r less than 1 was in a paper by Koenig and Stein, and independently by Torres and myself. So this is the same theorem, but in a different, actually, independently done. We did not know they were doing it, and vice versa. So this thing will handle the case where high-low or low-high. And then you left the difficult case where xi and eta have the same order. Well, in this case, you look at one frequency, say one dyadic frequency, and then you can you can put in a bump that has like compact support. So I can go ahead and erase that. Of course, you cannot do this because xi plus eta can actually, vanish, and you don't have one that's bigger than the other. So what you want to do is you want to expand this function in Fourier series. That's the idea. So you look at it in the dyadic frequency, and then you expand it in Fourier series. When you expand it in Fourier series, it will have, eventually you'll write it as a sum of terms times exponentials. These coefficients, you can compute the decay, because you know how much smoothness the function has, and the decay will be essentially this one for the coefficients. And the exponentials have the magic property that the exponential applied to a sum splits. And then the exponential can put one here and the other one there. And so that's the idea. But you have to, the coefficients are a little bit limited, so you have to see how much you can add, or to what power can you raise. Well, you can, LR, this proof works for all R, bigger than 1, less than 1. For R less than 1, you use the inequality that a sum is subadditive if you raise the power R. For R bigger than 1, you use the subadditivity of the LP norms to deal with each term separately. And then you'll reduce it to some estimates about little Pelly operators that some of you may know something about. So it reduces to little Pelly theory But unfortunately, the little Pili theorem will give us some extra term, which will, anyway, it has a constant. The constant depends a little bit on the parameters. And if it grows too much, then you're not going to have the convergence because the coefficients have limited decay. So there is, what we did in this paper was to obtain a very delicate formulation of this theorem in which the constant is under control and is only logarithmic in the parameter involved. And that logarithm doesn't destroy the decay there, and then we're OK. I mean, you know, so that's basically the idea in a few words. So I just want to point out that there's still one little tiny question open here, the case where p equals 1 and q equals infinity, in case we know it doesn't go into L1, but it could, that we know. So that's why we know the full range. But it could go into weak L1, which is a little bit bigger. That we don't know yet. So with that, thank you. No, you cannot have them all be equal to.
I know, so but I'm used to seeing results where you require F and G to be an L infinity, for instance, or S to be
Okay, Alex, one moment. So if P and Q are 2, R will be 1. Is that what you mean?
in your inequality, replacing the Q norm of G and the Q norm of F by infinity norms, for instance.
Yeah, it works with infinity.
Yeah, so that's what I'm used to seeing.
Yeah, but you know, it works with infinity. But there's I mean, I know applications where this do not need to be infinity. Because I know I had an application where the function was a log, so it was not in L infinity, but it was in every other LP. So I had to take a P that was less than infinity. You know, that happened, for example, in my research. So it doesn't need to be infinity.
Okay. I mean, does this recover? I mean, at least like the results that say when a product of functions in a Sobolev space stays in the same Sobolev space. Usually, I mean, people assume an L infinity condition or that S is bigger than your N over 2.
It's not necessary.
So does this recover that?
Yeah.
Though?
You see, this is the Sobolev inequality. This is Hölder's inequality for Sobolev spaces, and this is the only restriction. That's all I'm saying.
Really nice. I like it.
Thanks.
Any other questions? So this is actually an estimate on a tangent multiplier, right?
On a what?
A multiplier.
Actually, a multiplier is supposed to be bounded. This is not really bounded, but you can think of it as a multiplier in an extended sense, maybe.
And I was just wondering whether there's a class of multipliers, differential operators, more generally, for which there's not continuity, just continuity, but some kind of estimates involving, as you have, sort of algebraic expressions in the terms using multilinearity in some way. Does this fall into a class of more general results, or are they just very hard to get as you think of it more?
No, not hard to get. You can replace this by a pseudo-differential operator, for example, sigma of xc, and the proof would not be different, I don't think. But the theorems there, for example, this theorem's a little bit more stringent. I have some other conditions.
Okay. So there's some messing around with difficulties, but maybe similar.
You think of this as a symbol of a pseudo-differential operator.